Welcome. We have seen that the sun is continuously emitting radiation, and the energy that the sun obtains from the gravitational contraction is not sufficient to provide enough energy for this to support this radiation for a period of around 10 billion years, or at least 4.5 billion years, which we know is the lifetime of the solar system. So, the question then arises, what is the source of energy of the sun? And today we are going to discuss this question, what is the source of sun's energy? And I have told you that this source is hydrogen burning. So, the main process is called the PP chain, proton-proton chain. And in this process, protons are converted, so hydrogen is converted into helium through the PP chain, proton-proton chain. And this process becomes effective at temperatures greater than 5 million Kelvin. And the temperature at the core of the sun is around 1.6 into 10 to the power 7 Kelvin for the sun. So, we expect this mechanism to be functional in the core of the sun. The core of the sun, the solar constitution, at the beginning we know that it is 71% hydrogen, 27% helium, 2% heavier elements. Which in astrophysics is known as metals, are known as metals. So, anything heavier than hydrogen and helium we refer to as metals, and this is the standard solar abundance. This is what is referred to as the standard solar system abundance. So, this is the abundance of elements that we have in the solar system, and this is the abundance of elements that the sun started out with. But at present we believe the constant burning of hydrogen, the constant through the PP chain, the constant conversion of hydrogen into helium has modified this. So, the present abundance is quite different, and at present the abundance is around 36%. So, at present it is around 36% hydrogen at present. Okay. Now, the PP chain has several possible pathways. There are a variety of pathways, different paths through which the PP chain can finally convert hydrogen into helium, and we shall start off by discussing the most probable pathway. Okay, the most probable pathway. So, this diagram here shows you the most probable pathway in the PP chain. Okay. So, you should bear in mind that there are other pathways possible, this is only the most probable pathway. So, in this the first step you start with hydrogen, and bear in mind that the entire gas inside the sun is ionized. So, you have essentially got protons and electrons free. So, you start off with protons, and 2 protons, they collide with each other. We have discussed how this happens, they essentially you require tunneling. So, they collide, two protons collide with each other and they form some short lived intermediate state, unstable intermediate state. That intermediate state decays, and as a consequence of the decay you get this isotope of hydrogen which has got called deuteron. Okay. So, two protons produce deuteron. Okay, this is 2H. This is a hydrogen isotope which has got one proton, one neutron. So, you form one deuteron nucleus and there are two other products which are other particles that are produced in this nuclear reaction. So, you have this particle E plus. So, this is 2H. Then you have this particle which is denoted by E plus. Okay, I shall come to this E plus later. You produce this is a positron and you produce a neutrino. So, you have this nu E, this is a neutrino. And this particle is an electron neutrino. Okay, there are three different kinds of neutrinos, neutrino species which are possible. It is now known that there are three different species of neutrinos which are possible, and for each different kind of neutrino you also have its associated antiparticle. So, you have three kinds. You can have a mu neutrino, a tau neutrino, or an electron neutrino. And in this reaction there is an electron neutrino that is produced, and the neutrino is a neutral particle which interacts weakly with the rest of the material. It interacts only through the weak interaction. So, the neutrino in all probability just escapes from the interior of the sun and just passes through the entire sun and comes out. Okay. So, the energy that is carried, that is there in the neutrino, the energy in the neutrino is somewhere below 0.42 MeV, mega electron volts, and the neutrino which is produced at the core of the sun. So, the entire reaction is taking place at the core of the sun, somewhere in this region, and the neutrino does not interact, it is a very weakly interacting particle. So, in all probability the neutrino just comes out. So, the energy which is there in the neutrino is lost, it is not transferred to the rest of the material of the sun. Okay. So, there is one neutrino produced, an electron neutrino, and the neutrino when it is produced, it just goes out of the sun carrying away whatever energy it has, and the energy in the neutrino is less than 0.42 MeV. It could have a spread in values, this is the highest value it could have. Okay. So, that is one of the products of this reaction, of the first reaction in the PP chain where two protons combine to give you a deuteron. The other product is a positron. So, let me also go through this. So, the other product is E plus. This is the antiparticle corresponding to a proton. So, this is antimatter, sorry, corresponding to an electron, antiparticle corresponding to electron. So, it has the same mass and it is a spin half particle, same exactly opposite charge. So, it has the same mass. So, its mass is that of the electron, okay. Spin is half and charge is positive, exactly opposite that of the electron. And this particle, when it is produced, it propagates and it interacts with the electrons and which are there in the interior of the sun. So, it is ionized inside. So, the electron, the positron, it is called a positron, this particle is called a positron. It interacts with the material outside, if it encounters an electron and interacts with it, then the two of them can annihilate and the result will be 2 photons. And the entire energy in these two particles is converted into the energy of these 2 photons. So, whatever rest mass is there in these 2 particles and whatever kinetic energy they have is all converted into the energy of these 2 photons. 2 photons are produced. Okay. Now, the rest mass of electron and positron, we know this number, it is so the mass, the rest mass m, okay, m c square, m electron c square is 0.511 keV. Okay. The kinetic energy of the typical electron inside is around 1 keV at 10 to the power 7 Kelvin. I have told you the temperature inside is around 10 to the power 7 Kelvin. So, the kinetic energy of the electron there is around 1 Kelvin, which is negligible compared to this. So, it really does not contribute. Okay. The positron that is produced may have some kinetic energy. Well, the photon, so the 2 photons, the energy of the 2 photons that are produced is roughly greater than at least 2 m e c square, and it is so it is greater than or equal to, it is roughly of this order, it is 1.022 electron MeV. So, these are gamma rays, 2 gamma rays are produced. Okay. And so, these particles that are produced, these gamma rays, so the positron gets converted into a gamma ray, and this gamma ray that is produced basically will again interact with the material inside and transfer whatever energy is there to the material inside. It will not escape. We have seen that already, right. The mean free path is extremely small. So, this photon that is produced inside will transfer all its energy to the material inside. Similarly, the deuteron atom also will, if it has any excess kinetic energy, it will be distributed amongst the material inside. So, energy gets transferred to the material inside in this process. Okay. And the next stage in this reaction, let us in the chain of reactions. So, in the next stage what happens? In the next stage, this deuteron again collides with another proton. This is a hydrogen ion. So, this deuteron nucleus again collides with another proton, and as a consequence of this reaction helium is produced, an isotope of helium, an unstable isotope, helium 3 is produced, not the most lowest energy one, but an isotope with a higher energy, helium 3 is produced, and there is a photon also produced in this reaction. Okay. So, some more energy is released in this reaction, and the energy in the photon is transferred to the material inside. Now, so we have produced helium 3, and in the third stage of the reaction what happens is that 2 helium 3 nuclei. So, you have one such thing being produced, and again the same thing, suppose another helium 3 is produced. So, 2 helium 3 nuclei, they will collide, and these two helium 3 nuclei will collide to form a helium 4 nucleus, and 2 more protons are released. Okay. So, this is the most probable chain of reactions in the PP chain. Okay. There are other pathways which we shall, some of which we shall discuss, but this is the most probable pathway in the PP chain. Okay. So, let us briefly discuss what is happening. So, we have, let us just look at this again. So, we have two such reactions taking place, not so in each of these reactions two in each of these reactions two hydrogen atoms, they combine and produce deuteron, then produce helium 3, and then you have helium 4 forming. Okay. So, let us just make a brief summary of what is the end product of this entire chain of reaction. So, the end product, the final outcome of this entire chain of reaction is that you have 2 hydrogen atoms, and then you have 3 hydrogen atoms. So, 3 protons. So, 3 hydrogen atoms, and then you require 2 of these reactions. So, 6 hydrogen atoms. It is only the nuclei which participate in the reaction, but the electrons are there. Okay. The whole sun as a whole is neutral. So, 6 hydrogen atoms to start with, and at the end you have 1 helium 4. So, you have these are each 4 helium, and you have 2 hydrogen atoms in addition to this. So, you have 2 times 2 hydrogen atom. Okay. This is the overall effect. So, if you think of if you want to really think of the overall effect, 4 protons or 4 hydrogen atoms, 4 protons get converted into 1 helium 4. That is what happens. 4 protons get converted into 1 helium 4. 2 hydrogen atoms here and here, you can just forget about them. Okay, they are just intermediate. Now, any reaction, we know any such nuclear reaction or any reaction for that matter is governed by certain conservation laws. So, let us see what the conservation laws are here and how they are being actually how the reactions that we have been discussing are quite in keeping with these conservation laws. So, the relevant conservation laws over here, let me write it down. So, there are 4 relevant conservation laws. The first one is the conservation of baryons, of the baryon number, and baryons we mean protons, okay, neutrons, these are baryons. So, let us see if this is conserved. So, to start with, we have 4 protons. Okay. So, here we have 4 protons. So, we have 4 protons, and it goes to 2 protons plus 2 neutrons. The helium 4 has 2 protons and 2 neutrons, right. So, we see that the baryon number is conserved. Okay. The baryon number is conserved. So, we can put a tick mark here. Okay. Let us see next. Next we have the lepton number has to also be or the charge. Let us look at the charge. The charge has to be conserved. Okay. So, the conservation of charge. So, here we have 4 protons, which have 4 positive charges, okay, 4 positive charge. Here we have only 2 protons and 2 neutrons. So, there is an deficit of 2 positive charges, but these 2 positive charges we know are being carried away by the 2 positrons, right. So, we have 2 positrons also being produced, which are carrying away. So, this is also conserved. Right. So, 2 protons, we have 4 protons, and in the we have 2 protons and 2 positrons. So, the charge is also conserved. Okay. Then we have the lepton number, lepton. So, lepton number is associated with the electrons, neutrinos, etc. And the antiparticle have a lepton number of -1, the particle has a lepton number of +1, that is the convention. Okay. So, let us analyze this reaction. So, to start with, if you take the protons, there are no leptons associated with it, and you finally produce protons, neutrinos. You also produce 2 positrons which have got negative lepton number, but you also produce the neutrinos. So, you produce 2 positrons and you produce 2 electron neutrinos which balance the lepton number, right. This is an antiparticle, so it has lepton number -1, so this is -2, and this has a lepton number +2, so these two get balanced. Okay. So, baryon number, charge and lepton number, these are all being conserved in this in these reactions. You also have the conservation of energy. So, you have to bear in mind that the rest, when a particle is at rest, it has rest mass energy mc squared. So, any particle at rest has rest mass energy mc squared. In addition, it can have energy if it is more energy if it is moving. Okay. Now, the total energy is conserved. Now, in this reaction, so if you start off with particles which have more energy, more rest mass than the end product, the difference in rest mass gets converted into the energy which is released to the sun. That is the source of energy in this reaction. Okay. And in this process, one has to also be a little careful and take the electrons into account, into the account. So, essentially one has to look at the energy difference between 4 hydrogen atoms and the end product is 1 helium atom. Okay, that is the energy which is released in this process. The difference in energy is released actually to the either in the form of kinetic energy of the end products or through some other particles which carry away the energy. Okay, and we shall come back to this energy later today. Okay. So, this covers the main chain, chain of reactions in the PP chain, but there are other possibilities. Okay. So, this is the most probable possibility. There are other possibilities. And there are not 1 or 2 other possibilities, there are many other possibilities. So, here we shall only be discussing the most some of the more probable ones. Okay. So, the most probable one we have already discussed. So, we will amongst the lesser probable ones, we shall be discussing the ones which have still somewhat more probable, which are somewhat more probable. There are many more which are extremely improbable, which we shall not be discussing at all. Okay. So, let me now show you so there is right at the beginning you want to produce this helium 3. So, there is another pathway by which you can produce helium 3, and this pathway is shown over here, and this is the PEP chain. This is called the PEP chain. Okay. So, you can go from here to here either through the PP chain, which involves the collision of two protons, or there is an unlikely there is a less likely possibility where you have two protons and an electron. Okay. So, they combine and they combine to produce again a deuteron plus just a neutrino. There is no positron here. Okay. And there is a neutrino produced in this reaction. The energy of the neutrino is 1.44 MeV, and this 1.44 MeV, you see the neutrino here has a much lower energy as compared to the neutrino in this. So, this 1.44 MeV is easier to detect from the earth, right. The neutrino we have seen will just come straight out. The neutrino, as I have told you, will not interact much, it will just come straight out. So, we can actually probe these neutrinos from the earth. If you have neutrino detectors, you can probe these neutrinos from the earth, and this 1.44 MeV neutrino, high energy neutrino. So, it is easier to detect the higher energy neutrinos. So, this is amenable to easier detection on the earth. Okay. So, this chain, though it is not important for the production of helium 4 or the energy release in the sun, it is important if you want to look at the detection of neutrinos. Okay. And the percentage shown over here essentially tells you what fraction of the helium 4 is produced by this path and what fraction is produced by this path. So, you can see that extremely small fraction is produced by this path relative compared to this. Okay. So, both of these paths give rise to deuteron, and then the deuteron, again there are several paths which can occur from here. So, 85% of the helium is produced by the reaction where the deuteron the helium 3. So, this is common to all of them, but 85% of the helium is produced by the mechanism where two helium 3 combine to form helium 4 with the release of two protons. Okay, 85% of the helium 4 is produced this way. But there are other pathways. So, let me show you these other pathways. So, we are starting from here where you already have helium 3 produced. So, this is the pathway which we have discussed. 85% of the helium 4 is produced this way, okay. But there is another pathway here, and in this pathway, okay, let me first discuss this pathway. In this pathway, the helium 3 collides with one proton straight away to produce a helium 4, and in this reaction one positron is released and there is a neutrino released with again high energy 18.8 MeV. Okay, but this reaction, the very small fraction of the total helium is produced in this path, very small fraction. Okay. So, we have discussed this path and this path. There is a third path. In the third path, the helium 3 which was there collides with the helium 4 which is already existing, and in this collision you form 7 beryllium, okay, and a photon is released. So, 15% of the total helium is produced through this pathway. Now, having reached here, there again are two paths, and the bulk of the reaction in this path occur this way. So, here the beryllium 7 collides with an electron to form lithium 7, okay, it captures an electron to form lithium 7 with the release of one electron neutrino, and the energy of this neutrino could be these two, either of these two values. And then this lithium 7 could again collide with a proton to form two helium 4 nuclei. Okay, and in this path the bulk of the helium is produced this way. But again here there is another possibility, again a very small fraction goes into this path. Here the beryllium collides with the proton to form boron 8 boron, and this 8 boron then becomes beryllium with the emission of a positron and a neutrino, this is beta decay, and this beryllium then gives rise to 2 helium 4, okay. And there are neutrinos emitted in this, and these neutrinos, the energies are given over here. Okay, so there are a variety of pathways by which hydrogen goes into helium. I have told you the most dominant pathway in the pp chain, but there are these other alternatives also which involve beryllium, boron, etc. Okay. And there are neutrinos produced in these pathways. And now there is a branch of astronomy called neutrino astronomy, very important branch. So, the astronomy that we have been discussing till now is all based on the study of electromagnetic radiation from sources, but one could also study neutrinos. This has been possible only in the recent past, where you study neutrinos coming from distant astronomical sources, and the sun is the is the strongest source, nearest and strongest source of neutrino, nearest, okay, nearest to us. So, much of neutrino astronomy is studying solar neutrinos. So, the neutrino astronomy allows you to directly probe the interior of the sun as it is now, right. The neutrinos are produced in the interior of the sun. So, neutrino astronomy allows you to probe directly the interior of the sun as it is now. It does not, the photons produced inside, we have seen, take around 20,000 years to come out, they diffuse out. But the neutrinos, they do not interact much, they are weakly interacting particles, so they come straight out. And neutrino astronomy lets you probe directly into the core of the sun, where these reactions are going on. Okay. And the fluxes and energies are roughly consistent, okay, with our idea of the solar interior, which we have just outlined the reactions. Okay. And a long standing 50% deficit. So, there was a 50% deficit long standing. This was a big problem in solar neutrino, the study of solar neutrino, that the neutrino flux was found to be 50% smaller than what is predicted by these calculations. So, if you calculate the rate at which you expect these reactions to produce neutrino, it was found that the measured fluxes were 50% less. This is now understood to be a result of the conversion of electron neutrino to other types. So, there are the mu and tau neutrino. So, the 50% deficit is now understood to be because of the conversion of electron neutrinos to other type of neutrinos during its propagation inside the sun. and most of the neutrino detectors are sensitive to the electron neutrinos. So, they were missing out the neutrinos because they were being converted into other type, into the mu or tau neutrino. Okay. So, this is also now understood. So, I have told you about the main chain of reaction that takes place in the sun, where two protons collide to form helium. But there is another possibility, which is another possible mechanism for the nuclear reaction. Let me also go through that. That is called the CNO cycle. Okay. CNO, because this reaction, chain of reactions, involves carbon, nitrogen and oxygen. Okay. So, I have told you that the sun has 2% heavy metals. So, that 2% includes carbon, nitrogen and oxygen. So, there is another reaction pathway where the proton can combine with these carbon, nitrogen and oxygen to produce helium. So, let us go through that also. Okay. So, in this CNO cycle, what happens? You start off with carbon 12 colliding with one proton, and this produces nitrogen 13 and a photon. Now, this nitrogen 13 then does beta decay, and in this beta decay it produces carbon 13 and a positron and a neutrino. Okay. Now, the carbon 13 then collides with the proton to produce nitrogen 14 and a photon. Nitrogen 14 then collides with the proton to give you oxygen 15 and a photon. Oxygen 15 then again does a beta decay, it becomes nitrogen 15 plus a positron and a neutrino. The nitrogen 15 then collides with the proton to give back carbon 12. Sorry, this should be this has been typed wrong, this should be helium 4. Okay. So, this 16, so this should be helium 4, not hydrogen. Okay. So, there is one helium 4. So, the last reaction should read 15 nitrogen plus 1 proton, this goes to carbon 12 plus 4 helium. Okay. So, please make this correction. That is the last reaction in this chain. So, the net effect you see is that you start with 4 protons and you produce helium 4. Okay. Carbon, nitrogen and oxygen, they basically act like some kind of catalysts. They are required for the reactions, but at the end you are back with where you started as far as these are concerned, with where the carbon is concerned, and you end up producing helium from 4 hydrogen atoms. Okay. So, you have this reaction, and this reaction is more effective at higher temperatures. We shall come back to this issue. So, this is more effective at higher temperatures. And stars which are more massive than the sun have higher temperatures inside. So, the CNO cycle is more important if you go to more massive stars, stars which are more massive than the sun, whereas the PP chain is more important for low mass stars like the sun or even lower masses. Okay. So, there are these two possibilities, and if you go to high mass stars, stars which are considerably heavier than the sun, then you have more of the CNO cycle, less of the PP chain, whereas in stars like the sun you have more of the PP chain, less of the CNO cycle. Okay. So, in both of these reactions you have 4 hydrogen 4 protons, you have 4 protons, 4 hydrogen atoms going into sorry, let me write it correctly. So, you have 4 hydrogen atoms going into helium 4. So, let us see how much energy is released in one such reaction. Okay. So, we have to look at the difference in masses. between this. So, one hydrogen atom has a mass 1.00783 atomic units, whereas one helium 4 has mass 4.00260 atomic units. One atomic unit is 1.66053 into 10 to the power minus 27 kg. So, what we have to do is we have to calculate 4 mH minus m helium into C square, right, 4 times the mass of a hydrogen atom minus the mass of helium, and you can see that there is a considerable difference between these two. This is the energy which is transferred to the material in the sun, which is the energy which is released in this reaction, not necessarily transferred. The part in the neutrino is just lost, okay. The rest of it is transferred to the sun.
So, and the positrons?
They also transfer the energy to the sun.
So, we are not taking that.
No, but positrons are produced in this, right. So, the energy difference is essentially what goes into the part of that goes into the positrons. So, right, but that mass again gets annihilated and converted into radiation, which is transferred to the sun. Okay. So, at the end you do not have these positrons hanging around. So, all the energy in the positron has been converted into the energy of the sun. Okay. The electron also gets annihilated in that process. Okay. One of the electrons in the hydrogen atom. Finally, you start off with 4 electrons, you are left only with 2 electrons. Okay. So, all of that has gone into this. They are all converted into, that is all of this mass is converted into energy. Okay. And if you put in the values, I have given you the values here, then this comes out to be 4.29 into 10 to the power minus 12 joules, that is the energy released in one such. So, if 4 hydrogen atoms get converted into 1 helium, then this is the energy that is released. You can calculate it yourself putting in these values, and this is also equal to 6.75 MeV. Now, the quantity which is of more interesting is the fraction of the mass that gets converted into energy. Okay. So, let us look at this. So, we want to calculate, this is the energy that is released and divided by the mass of 4 hydrogen atoms. This is the ratio of the energy that is released to the mass that you started with, okay. And this comes out to be 6.4 into 10 to the power 14 joules per kg. Okay. So, if you take 1 kg of hydrogen and put the entire 1 kg through the pp chain or the CNO cycle, you will produce 6.4 into 10 to the power 14 joules of energy. Okay, it is an enormous amount of energy, and okay, and just if you just make an estimate, 10 grams of hydrogen are sufficient to provide all the fuel that an individual living in an advanced country, not in India, our fuel consumption is extremely small, okay, but 10 grams of hydrogen is adequate to produce all the energy that an individual living in a developed country requires in his entire lifetime. okay, just 10 grams of hydrogen. Okay, so you will appreciate the how efficient this nuclear fusion is as a source of energy. So, if you could have controlled fusion on earth, which has not yet been possible, but if it could be achieved, then a very small amount of hydrogen would be enough, adequate to provide the energy requirements of the entire earth, okay, which the sun is now doing that. Sun is now providing us the energy, but we are not able, we are able to tap only a small fraction of it. Okay. So, this is the energy that is released in one such, okay. So, per kg. So, if I can take 1 kg and go put it through this reaction, this is the energy that will be released. Now, let us estimate the total energy that will be released by the sun, okay, total energy that will be released by the sun. So, to do this estimate, so we know the mass of the sun. So, this is the sun, we know the mass of the sun, okay, and but only a small part of the energy is actually going to be burned into hydrogen. So, we will assume that 10% in this core gets converted into hydrogen, the outer parts do not participate in this reaction. Okay. So, that will be a, so the mass of the sun is so the mass of the, okay, so if I can take 1 kg, let us start off this way. If I take 1 kg and I will get 6.4 into 10 to the power 14 joules by kg. The mass of the sun is 3 into the mass of the sun is 3 into 10 to the power 30 kg, okay, and then 10%, so into 0.1, and 2% of the energy is lost in the form of neutrinos. So, we take another factor of 0.98, okay. This should be 2 into 10 to the power 30 kg, okay. So, this gives us no, this should be 3 into 10 to the power 30 kg, which will give us these many joules. That is the joules of energy available. Okay. So, what have we done? This is the energy that will be released if we can burn 1 kilo of hydrogen. The mass of the sun is 3 into 10 to the power 30, and 10% of that in the center is going to get converted into helium, and 98% of that is going to get transferred to the sun. There is another factor which I should include, and that is a factor of 0.71, because 71% only is hydrogen and the rest is helium. Okay. So, we start with the we have the starting ratio of hydrogen abundance into the mass into the fraction that can actually get converted into helium, the fraction in the center, the fraction of the energy that is transferred into the energy that is transferred per every kilo, converted per every kilo, and this, if you combine all of these factors, you will get 1.3 into 10 to the power 44 joules. Okay. Now, we can now estimate the lifetime of the sun. How long do we expect the sun to last? So, this will be 1.3 into 10 to the power 44 joules divided by 2.6 into 10 to the power 26 watts, which comes out to be of the order of 3 into 10 to the power 17 seconds, okay, which is of the order of 10 to the power 10 years, okay, and which is more than the known age of the solar system, 4.5 billion years. Okay. So, the nuclear fusion, the conversion of hydrogen to helium has adequate energy to power the sun for something like 10 billion years. Okay. Finally, let us now look at the energy that is released. So, the rate, the energy release rate, the reaction efficiency. Or the energy release rate. Okay. Now, the rate at which energy is released in this reaction, that depends on the number of projectiles for any reaction. It depends on the number of projectiles. So, we have these particles. The way we think of it is, we have these particles and there are some other particles incident on them. So, it depends on the number of incident particles and it also depends on the number of targets. So, in this case, the number of projectiles is the hydrogen abundance for the pp chain, let us say it is a hydrogen abundance into the density of hydrogen, and the number of targets is also the hydrogen abundance into the density of hydrogen. So, it is proportional to x square rho square, and if I ask what is the rate at which energy is released per kg of the hydrogen, then I have to divide by the density of per kg of the star material, then I have to divide by the density, and this is of the, so then this is the dependence. So, we can quantify the energy release rate in this way, that is how it is normally done. Okay. So, this tells you the rate at which energy is released per kg of the material, okay, per kg of the material, and it depends on the hydrogen abundance squared. There is a constant over here, roughly constant, a number which is roughly constant for the temperature range of our interest, and it depends on the density of the at the center of the star, and it depends on the temperature on the at the center of the star in units of 10 to the power 7 Kelvin, density in units of 10 to the power 5 kg, temperature to the power beta. Okay, the temperature dependence is not linear, it is sum to the power beta. I have told you that the temperature dependence is extremely, it is a very sensitive dependence on temperature. Okay. And for the sun, okay, not for the sun, for the pp chain, beta is known to have a value around 4, and for the CNO cycle, beta is known to have a value around 15. So, the CNO cycle has a very strong dependence, the efficiency of the CNO cycle or the rate of which the energy is released through the CNO cycle has a very strong dependence on the temperature, okay, and it becomes much more effective at higher temperatures. For the sun, the value, the energy released per the rate at which, so this has a value watt per kg. Okay. These are for the parameters of the sun, which I have already told you the values. Okay. The temperature inside the sun, the density inside the sun, etc. Okay. For the sun, 10% of the burning is through the CNO cycle, the rest is through the PP chain. But for more massive stars, the CNO cycle is much more effective. Okay. And this is where the PP chain is effective, and this is dominated entirely by the PP chain, and if you have these temperatures, it is the CNO cycle becomes dominant. Okay. So, in more massive stars where the temperature is higher, the CNO cycle is much more dominant. Okay. So, let us bring today's discussion to a close over here. In today's class, we learnt essentially the reactions that are responsible for producing the energy in the core of the sun, and I told you that there are several pathways through which this reaction can take place, and I also discussed what is the most dominant pathway that is taking place in the center of the sun.